All right. So I think for the better part of last week, um, when we started the lecture, we started looking at slabs generally, and one of the things that we were focusing on was to pretty much understand what slabs were. All right. And I did mention that slabs are, or in terms of slab design, generally the design is similar to that of beams. All right. Very similar to that of beams. So whatever we've done with regards to beam design, we do something very similar to slab design. All right. Just want to join the link from here. Oh, you're not working. Okay. All right. So I did mention that all right, just a second. Okay, so yeah, so we started looking at slabs, and the goal is okay. So we mentioned that when it comes to slab designs, there are different ways by which you can look at it. So I started breaking that down into this format. Now we can have simply supported slabs. All right. So let's say you have a wall, maybe you have a wall and a wall, and then you have your slab right over it. A typical example would be the overhead uh, concrete water tank support, right? So you have your Rambo poly tank sitting right on it. Okay. And some might have beams, all right, but some could just have two walls, okay, right there. Okay. So the slab, pretty much, if you look at the slab in terms of its behavior, this is how the slab looks like. Okay. So this is your slab, and this could be the wall. Okay. It could be wall or it could be beams, depending on how the design was done. So the analysis process. Recording in progress. Oops. So the analysis process is very similar to that of beams. Then we can, so with a simply supported, we either have one way or we have two way. And one way or two way, it's dependent on how the loads are being, what's the name? The loads are being transferred from the slab to, or how the load are being distributed. That's a better word. How the loads are being distributed. All right. And that's whether it's one way or two way. And we also have continuous slabs. All right. Which are slabs which span over supports, right? And we looked at a typical example being either the panel system, the panel-based system, where you have a series of slabs spanning over a series of beams or columns or whatever. Then we have the case whereby it's just one straight panel, where that will lead to a one-way load distribution approach. All right. So we have like we have in total four different considerations when it comes to slabs. Either we are looking at one-way simply supported, two-way simply supported, one-way continuous, and two-way continuous. All right. So we'll try and solve some examples to see how best all of these things tie in, and then how the rebar arrangement is done. Okay. So that's what we looked at last week. One other thing we focused on was what we determined as is my internet going off? What's wrong with my internet? Can you guys hear me? Okay.
Yes, sir.
Okay, all right. Because something funny just happened to my other PC. All right. So we look at the span to effective depth ratio. All right. We normally, when you have any design or you have any structural member and you apply some loads to it, what happens is that it will deflect. Okay. And deflection is important to us. Okay. You spend a greater part of your second year looking at how to calculate deflections, right? Either the geometric methods, the virtual work method, and some other forms. And these or like Castigliano, and these deflections, if they are very high, especially for slabs, they tend to damage the ceiling if you have some POP works or plasterboard ceiling. They'll end up deforming or breaking, all right, because they are quite brittle. They'll end up breaking if your ceiling deflects beyond certain levels. And also, if let's say there's a floor finish, maybe you have some tiling and then all of that on the floor, or maybe some wood panels on the floor, they can also deflect because the floor is deflecting. All right. And you wouldn't want that because at the end of the day, uh, when it comes to putting up a structure, it should be safe. All right. And one aspect of the safety has to do with perception. If the occupants perceive or feel like the building is not safe, they will not use it. It could be structurally safe and all of that. But because of that feeling, that perception by the occupant that the building is not safe because maybe they are seeing some visible deflections on your slab, that means that the building will not be able to fulfill its function. Okay. So we limit how much deflection we can have. Okay. And because usually for slabs, the depth of the slab is very small, right? It is very small. We need to actually, even for beams, we do the same thing, but particularly for slab, we need to know from the onset which depth of the slab will be adequate for us, which will pass both the bending and also the deflection tests or the deflection requirements. Okay, you don't want to finish your bending, find your AS, and find your M, find your AS, and then also do the detailing and whatever, or find the reinforcement, and then later you come and do deflection check, and then you realize that okay, your slab is not passing the deflection check. Okay. And once it's not passing the deflection check, you have to go back and change the size of your slab. And once you change the size of the slab, you have to do the analysis of the the design of the bending all over. Okay. So from the onset, we look for a depth which will be okay, or which will be which can pass the deflection check. Okay. So that's how come we look at what you call the effective span or the span to effective depth ratio. Okay. So the span is usually the distance normally or usually it's taken as the distance between the centers of the support. So this is your span. Okay. Some have span as the clear length plus the D, but let's forget about that for now. Maybe I'll write that into going forward. Okay. So how do you determine your D, your effective depth? Okay. The span, you know the span. You know how far, how wide your slab is with respect to the support, and also an idea as to how, or you also have your rebar arrangement and all of that. Okay. So normally, since it's a ratio, so you find span over the effective depth. All right. And the code has a limit as to what the ratio can be. Okay. So if you check table 3.9 in the BS 8110 or 8110, as I will say, if it's a cantilever and then the cross section of the slab or beam is rectangular, then the limiting factor for span to depth is 7. Okay, so which means that so normally when we are dealing with design, what we do is that, okay, if let's say the slab is maybe, okay, since I'm using a cantilever, let me go with that. So if let's say you have a cantilever, the span is maybe 6 meters. Okay, it says that your span to depth ratio should not uh be more than 7. All right. So that if your span is, let's say, 6,000 millimeters over the depth, which you don't know what value is, let's say it's equal to 7, then it means that your depth D is equal to 6,000 over 7. All right. So 6,000 over 7. Oh, I didn't bring my calculator. 6,000 over 7 is what? Can someone help me? Um,
857.
sorry, come again. 857. Okay. So it means that the minimum depth we can use is 857. So this is the minimum we can use. All right. Which means that we have to use a deeper and normally you wouldn't want your slabs going more than 200 millimeters in depth. Normally, you can do more than 200 anyways. But if you want to avoid shear design, you would want to go below 200, right? So this means that for this cantilever to be stable or to have structural integrity, the depth of this, so this D over here, which is the depth, should be more than 857 millimeters. I mean, like, this is like a crude way or basic way what we do. All right. There's a more elaborate approach, which I have in the lecture notes, but in crude way, this is what we do. Right. We quickly go to the table. What was the name? 3.9. Find the ratio. We know the span. We divide the span by the ratio, and then we find the minimum effective depth. So let's say the same beam, but now it's simply supported. The same span of 6 meters. Okay. If you go to the table again, say that it says your span to effective depth should not be more than, here it says 20. So 24 simply supported. So if it's 20, then it means that here I'm dividing 6,000 by 20. All right. And that'll give me what? 300, I guess. All right. So it means that this is the minimum I can use. I can use 300. Okay. So again, you can see that depending on the support conditions, your span to effective depth can also vary. All right. There is a more elaborate approach which we use, and this is the equation for that. Okay. So we say that the minimum effective depth D main is equal to the span over the basic ratio times what we call the modification factor. All right. So the basic ratio is from the basic ratio here, sorry, here is from this table. Okay. Then we have some modification factors on the side. Okay. So these modification factors, we get them based on whether we have tension reinforcement or compression reinforcement. All right. So because you would have to estimate the depth, the effective depth before you even start your calculations or your design, it means that at that point you might not know whether you have compression reinforcement or tension reinforcement. So most documents that have reviewed would inform you that, okay, you know what, or even in practice, what we do is that we just divide the span by the basic ratio. All right. And then whatever answer we get for the minimum effective depth, we just increase that by maybe some 25 or 50 millimeters extra to cater for when we get our when we get all our data and then we do our or the proper effective depth checking. All right, it should still pass anyways. All right. So the modification factors, they are based on two parameters. All right. If the slab has only or if there's only tension steel, right? So if there's only AS, we have a different table for the modification factor, and that is supposed to be table 3.10 or 3.10 in the BS code. That is for only when we have tension steel. Then if you have both tension and compression rebar, we go to table 3.11. All right. So I put in an example in our notes. All right, which goes like a continuous rectangular beam. It spans 12 meters with a mid-span ultimate moment of 400 kilonewton meter. So we have a moment, and we have a depth of 600 millimeters. Please, the depth of a beam and then the height of a beam are two different things, right? The height is the full height of the beam, and then the depth of the beam is the distance from the midpoint of the tension reinforcement to the top compression flange or surface or edge. Okay. All right. So here, if you go to table 3.9, since we are looking at a continuous beam, our ratio is 26. So just taking you up there, continuous beam, so ratio is 26. All right, and it's a rectangular section. If it were a flange section, the ratios would change, right? So 26. Now, I think I mentioned something, I didn't say it now, by the notes. Where is it? Okay. So the table 3.9 is for length up to 10 meters. All right. So once the length or your span length it goes beyond 10 meters, you have to modify even the basic ratio. So here I have the span length being 12 meters. So we have the span length of 12 meters. All right. So that exceeds the 10-meter limits for the basic ratio. So we need to modify the basic ratio. And to do that, we multiply the basic ratio by the limiting length of 10 divided by the actual span of your beam or slab. Okay. So that would further reduce your basic ratio to 21.7 instead of the initial 26 that we had from the table. Okay. So now our basic ratio is now 21.7. And now let's find the modification factors. All right. So we are being told that so here, the color change. Okay. So here, this is the compression zone, right? And the diameter of each bar in the compression zone is 16 millimeters. There are two of them. All right. So let's go and look at how to find the modification factors. All right. So let's look at table 3.10, which is for the tension. And the yield strength for the rebar is 460, right? We're getting 460 for the yield strength. So I come in here, I choose 460. You have to find M over BD squared. Okay. So your M is 400 kilonewton meter. Your B is given as 300. So here's our B, 300. And then the D is 600. Right. So we have an M over BD squared of 3.7. Okay. So using linear interpolation, you can find the the modification factor for what's the name for the tension. All right. So once we do that, we end up with 0.89 as our modification factor. Okay. Then we do same thing for the compression reinforcement. Okay. So for the compression reinforcement, that is table 3.11 in the BS code. Then we find 100 AS over BD. And this AS prime here is the area of tension steel you provided. It's not what you calculated or what you required, right? After you find the AS prime required, you go to your table or you do your calculations, you get your actual rebar sizes and their number, and then based on that, you get your AS prime provided. Okay, so that's what you use for these calculations. 100 AS prime provided over BD. Okay. So I think what I did my calculation, I had 0.22. So with 0.22, again, I have to do linear interpolation because 0.22 lies between 0.15 and 0.25. So once we do our linear interpolation, we end up with our modification factor for the compression being 1.07. Okay, so now we have two modification factors, one from the tension and one from the compression. All right. So what do we do? In this case, per the code, we multiply the two modification factors together. It becomes 0.89 times 1.07. Okay. So here, your ratio of spark to effective depth will be the modified basic ratio times the modification factor from tension and then the modification factor from the compression. So in all, you get 20.7. So what this means that this is the highest ratio we can go. We cannot go any value beyond 20.7 for the ratio. All right. So this becomes our limiting. So this becomes our limiting ratio. Okay. So now let's find the actual span to depth ratio. Our span is 12 meters. Our effective depth is 660 millimeters. So we find a ratio of that and we get 20. Okay. So since our ratio from the beam is 20, which is less than the 20.7, then our design is adequate, or our choice of the depth being 660 millimeters is adequate, at least against with respect to span to depth ratio. And this has an implication on your deflection going forward. Right. Once your beam passes or your slab passes the span to depth ratio check, most likely should also pass the deflection check. Most likely, not always, but mostly it should pass the deflection check. So this was an example that I looked at before my PC went off on me. I couldn't really, it was a bit of a challenge to go back and forth with it. Yeah. So I'll still post this video. I have it somewhere. I'm pretty sure I'll look for it. I'll post it and then you can add that to what we'll be looking at today. Okay. So for today, since we now know what modification factors are, now we can look at how to analyze flaps. All right. So we start by looking at design of one-way spanning So look at design of one-way spanning solid slabs. All right. So I'm just going to take you guys through an example, and then you see that the steps are fairly straightforward compared to what we had in the beams. All right. Anyways, how is the assignment going? I think it was due, right? It was due sometime this week. Are we all done with the submissions? Oh, I can't even check over here.
Yeah.
All done with the submissions. I only have 4 submitted. What's happened to the rest of us? So I have Daniel done, Prince done, Nathaniel, and then Jeff. Delali, no. Akwesio Odro, he's still with us. I don't know. Isaac, no. Is Dylan still with us?
Yes, sir.
And then Collins, no. So why are they not submitting their work? Collins, I think you are online, so you should be able to answer your the questions for yourself. Unless he's left. Oh, no, I'm left with 2 of us, anyways. Okay.
Hello.
Okay. All right. So let's continue. Um, try to bring up the example. Just give me a second. Before that, I'm just mention a few things so that we have some information. So, when we want to design the one-way spanning solid slabs, one of the things that we need to look at, see if I get the right spots to write this thing. Otherwise, no, I'm gonna stress my. All right. So we determine what's the name? The suitable depth of the slab. Okay. So here you can use just simply put the basic ratio under the span and then find the depth of it, because at this point you wouldn't have information on the reinforcement arrangements, right? Then two, we determine the, so here there are two reinforcements, the main, reinforcement and secondary. I will explain them going forward, okay? Then if need be, we check for shear. All right, we always have to check for shear. Check for shear stress. All right, so I can put some a series by that, and then of course, then you also do your detailing. All right, or slab detailing of slab. Uh, all right, so something like that. Okay. Um, so that's what we need to take note of. Um, so when it comes to spanning one way solid slabs, they are typically designed as if they are, or as though they are, or they consist of, what's the name? Of a series of beams of 1 meter width. Okay. I think somewhere around last week, either I mentioned it over here. Let me see if I have that same information up there somewhere. Otherwise, I have to put it in there. Like so, the width of slabs is already fixed on a unit width of 1 meter, right? So usually, as designing slabs, we assume that we're designing for a meter width of the slab length, because the slabs can usually be longer than 1 meter. They could be 2, 3 meters width, but standardized designs require us to use per meter width of the slabs. So regardless of what slab you're looking at, typically you're looking at only 1 meter of it, or a meter of the slab. Right. Then whatever you get, you can extrapolate it to the other length. Okay. So that's one thing. Design is up to 1 meter width. Um, the main steel uh, is in the direction uh, of the span. Then we have the secondary. So these are just information that will come across again. The secondary, or what you call it, the distribution. Rebars or steel. Those are usually required in the transverse direction. Okay. And normally when you're positioning the main rebar is always the most bottom or the most top rebar. All right. So that, for example, if you have let's say if this is your slab, if this is a cross section of the slab, right, you have your supports, could be beams, it could be walls, it could be columns, whatever they are. Your main bar, let me see if I can increase the thickness of this guy here. So this is just for exaggeration purposes. All right, so the green will be your main rebar. Okay, so this is a main rebar, and then the red will be your secondary rebar. Okay, so the main rebar is always closest to the bottom or closest to the top, and the reason is because we want to give it the maximum lever arm, right? So let me put that over here. The main rebar uh should form the outer layer of reinforcements. And this is let me just add this extra to give it the maximum lever arm. Okay. So the calculations for bending, it follows similar procedure as that of the beam. So let's look at an example. Let me put together an example, and then hopefully everything explains itself going forward. So have a slab. So example. Second. Okay, so let me put this together. So the slab shown below um, is to be designed to carry live load of 3 kilonewtons per meter squared. Plus floor finishes uh, and ceiling loads of 1 kilonewton per meter squared. All right. So FCU is 30 newtons per millimeter squared. Fy is 460 newtons per millimeter squared. So we are given that the basic span to effective depth is 20. So this should fall in the category of continuous. Sorry, in the category of simply supported. All right. So this is what we have for the beam. All right. So we have a beam, a slab. This is your slab. This is 4.5 meters. All right. So what do we do? We start by looking at so let me give the width of the beam or the wall. That's 230 millimeters. Okay, great. So let's look at a solution for this. Okay. So now let's find the effective depth, right? Before we do any calculations, we find the effective depth. And we know from so let's say find G, okay. So D minimum is equal to the span over basic ratio times the modification factors. That much we know. All right. So let's look at it. So this is going to be our span is 4,500. Right. Our basic ratio is 20. We don't have our MF. So if you don't have your MF, you can estimate what this value would be. All right. So here is going to be what? 225 over MF. Okay. So let's assume. So for now, let's assume that our MF is 1.3 for RC slab. Normally it's around this value, or anyways. So it means that my D minimum will be equal to 225 over 1.7, and that should give us what? Those were the calculators. 225 divided by 1.7. Well, so we can use that, let's say 1.7. That will give us 132. This is too small. Okay. 1.3, no 1.7. What am I doing? 1.3. 1.3. This will give us 173. So let's say, let's try D equals 170. Okay. Here we got D is 225. We can also say let's try D 200. All right. So if D is 200, or so sorry, if D is 170, so means that this is our slab. Right. So assuming there's rebar over here, then our D is from the top here to this rebar. Okay. We still don't know the height of this slab, or we are yet set. Normally design, you also determine the height of the slab. All right. So to determine the height of the slab H, it's a fairly straightforward process. Okay. So to determine H, which is the height of the slab, H will simply be what? D plus half the diameter of the rebar plus the cover. Okay. So again, for now, you're making assumptions. Again, in design, you make assumptions. You make quite a number of assumptions, but the assumptions are guided and guarded by the code of practice, which is the BS 8110. So every assumption you make should be justified. All right. So let's say we are using a 10 mm bar. So let's say phi is equal to 10 mm and the cover C is 25 millimeters. Cover to reinforcement. All right. So my H becomes 170 plus 5 plus 25. That's what gave me 200 millimeters. Okay, so my H, which is the what's the name? Is the overall depth of the slab, right? It's 200 millimeters. Okay. Why am I going through this? Because I need to calculate moments. All right. So to find moment, I need to know the overall depth of the slab. Okay. So let's look at to determine D2, determine load and maximum moment. All right. So we're told that the live load LL was given to us as 3 kilonewtons per meter, and the dead load, which is from, so let me put this way. This looks like L. So we are saying that what floor finishes floor finishes and ceiling load is equal to 1 kilonewton. This is per meter squared, sorry. Now we need to find the self weight of the slab, which were not given. All right. So to find the self weight of the slab, this thing that I'm going to do right now is an important component of design, right? The weight of the structure also adds up to the loads. All right. Previous examples, we have assumed that whatever dead load we had also included the self weight. For this example, we're actually finding the load coming from the self weight. All right. And to do that, we need to find the overall depth H times the specific weight. So H times specific weight of RC, reinforced concrete. And so that writes over here the specific weight um or, or some specific gravity is fine. Um weight or gravity is the same. And normally it's given as 20 uh kilonewtons per meter cube. Okay. So what's happening to my screen? This is always have a way of messing you up when you don't need them to. Okay, just a second. I'm going to reshare the screen. Uh, okay, so this is the height. We convert the overall depth to meters. So this is what 0.2 meters. I can put here 0.2 meters times 20 kilonewtons per meter cube. And when you do these calculations, you should end up with 4.8 kilonewtons per meter squared. Okay, so it means that your total dead load will be 1 plus 4.8. That'll give us 5.8 kilonewtons per meter squared. Okay, so here let's calculate the ultimate load. Uh, 1.4 GK plus 1.6 QK. So this becomes 1.4 times 5.8 plus 1.6 times 1. And then that would be equal to, am I correct? I'm hoping I'll be correct in the end. Someone can do it for me. I got 12.91 kilonewtons per meter squared. Am I correct? Let me see, 5.8 times 1.4, which is 8, plus 1.6, 29. I'm making a mistake. Oh, times, sorry. 1.6 times 3, not 1. The life load is 3. Okay, so maybe that's how come I got a different answer. Okay, so I get 12.92. All right, great. So I think I'm on the right path. So maximum moment will be WL squared over 8. That'll give me 12.92 times 4.5 squared, which is the length, over 8. That'll give us 32.7 kilonewton meter. Okay. So once we have this, Um, you can check if your beam needs compression reinforcement. All right. You can check that. You realize that it doesn't need it. Um, oops. So I'm going to do this right here. I'm jumping one step. I'll come back to that step. All right. So let's do K, which is equal to M over BD squared FCU. So that'll give you 32.7 times 10 exponent minus, sorry, 10 exponent 6 divided by B of 300 times a D of 170 squared. Our FC is 30, and that will give us, I think, 0.03, which is less than 0.156. So no compression still required. All right, let's take a note of that. Great. And because of this very small value of MB, no value of that, you realize if you want to find AS, where AS is equal to M over 0.87. So you've come across these equations before by just using the same equations because everything is similar to that of beams. This is M over 0.87 FYZ. All right. To find Z, we know how to find Z, right? Okay. You would realize that Z uh Z will be equal to 0.95 D. So this is 0.95 times 170. That'll give us 161. Okay. Always check Z. I mean, check Z by using the equation where Z is equal to D into bracket 0.25 plus square root of 0.5 plus square root of 0.25 minus K over 0.9. All right. So that's how we find Z. But Z has to be between the limits. The upper limit is 0.95 D, and then the lower limit is 0.775 D. Okay. So this here will be equal to 2.7 times 10 exponent 6 divided by 0.87 times 460 times 161. Right. So our AS here, or A sub S, will be 508. Okay. One thing I didn't mention is that since we are looking at per meter width, everything we are doing here is per meter per meter. All right. So finally, I'll show that here in the rebar. So it's 508 millimeters squared per meter length of the slab. Okay. So there's a table which I don't think I have it over here. Let me see if I can find it somewhere. Um, okay, I think I have a table here. Maybe we can use that table. Hopefully it's good table. What am I looking for? So let me just bring it here. Okay, hopefully everything comes. Let me paste it. Hopefully it pastes. So I should have it shown. All right. So we can use this table here to determine the rebar, and its corresponding spacing. All right. So we got 508. We are using 10 bars. So it means that we are going to look at this section right here. Okay. And the one that works well for us is this guy. So we end up with 150. So it means that I can write provide maybe in green so that we see that it's important. So provide, since it's a high yield, so we use 10 T, sorry, to represent high yield of 460. Provide T10. Let's say rebars at 150 millimeters. Okay. Since this one, we are looking at space in the centers, right? Where the ASP is 523 millimeter squared per meter, right? You would also have some documents or some books. So some would just say T10 at 150. Okay. Or even not many millimeters here. Okay. So some would just say C to C. It makes sentence, right? All right. And that's how we do the design the for the what's the name? For the bending. Now let's go back and check our now we have enough information to check if our span to depth ratio that we chose was fine. We chose as a depth of 170 so that we can go back. Since now we have enough data to do the proper analysis, we can go back and do all of that. All right. So here, let's say recheck. Recheck span to effective depth ratio. So here we only needed what's the name? Only so we'll go to table 3.10. Table 3.10 here. All right. So I like to always bring the table down so that at least we follow what we are doing. At some point I would stop, but it's just that for now, let's go with this flow so that we know how we go with it. Okay. So let's find m over bd squared. M over bd squared will be equal to our m, which was 32.7 times 10 exponent 6 divided by the b. Oops, what did I put for b in the first one? Oh, sorry, the b is 1,000. All right, it's a meter always for b is 1,000, please. B is always 1,000 for slabs. Right, not 300. I don't know where I got the 300 from. So it's 1,000 times 6. I think I have beams in my hand. Why? Times 171.6. What am I? What did I write for that one? Okay, times 170 is fine. It's correct. Then let me go back here. All right, so I have that one corrected. So it becomes 1.13. All right, so that's for our m over bd squared. Our fy is this value over here. So we are somewhere in between. So we are somewhere here, 1.13. So you have to choose somewhere between my eraser is annoying. Okay, so let me just go back and put this over here. we have to choose somewhere in between these two values. All right, so we use linear interpolation. I have described that extensively in previous lectures, so I wouldn't do that over here. All right, so if you find that, you would realize that your modification factor, MF, will be 1.34. Okay, to 1.34. So now let's see if what we did earlier makes sense. So our limiting ratio, okay, since that was the span, span over the effective depth, okay, which was same as the ratio 20 that we had times the modification factor, which is 1.34. That should give us 26.8. Okay. Now this is what we had, our actual ratio. So our actual ratio was again, that's also span over effective depth. So that would be equal to, the span was 4,500. All right. And then our depth was 170. So we should get a number below 26.8. Right. If it's above 26.8, that means that other we've done, we have to go back and then look at it. So this should give us 26.5. All right. So because this value here is not greater, or this, or the limiting value is greater than the actual value, then it is adequate. So here I can state that D equals 170 millimeters is adequate. Great. All right, so now let's check if we need shear reinforcement. It is important to always check shear. Mostly you might not need it because of the depth of the slab that we choose, but it's always good to, or it's best practice to always check for that. So number 5, check shear stress. All right. So let's look at the shear at the face of the supports. All right. So V at the face of support, VS. Uh, so going back here, this is our slab, and our UDL on it. Our UDL was what? 12.92. 12.9 is fine. So 12.92 kilonewtons per meter. This is 4.5 meters. And please take note, your support is 230 millimeters. Yeah. So you can find your reactions. They are easy to find over here. All right. So it becomes 12.92 times what? Again, calculator. Um, so 12.92 times 4.5 divided by 2. That is 29.07. So each one is 29.07, 29.07. So VS here, sorry, I don't know what happens to anytime this thing goes away. I tried to do What's the word I'm looking for? Okay, I think everything is back to normal. All right. So to find VS, it's going to be 29.07 minus half of the one way to look at it, we got 29 points. Let me just do the simple approach. 29.27 minus 12.92 times 0.23 over 2. All right. So they uh have this distance here. So let's see if what I'm doing this makes sense. Again, I'm doing this from my head, so I'm hoping that my calculations are good. All right. Otherwise, then we're in trouble. Yeah, so I think I'm good. So this will give me about 27.6 kilonewtons. So this is my V. So this is my so this is supposed to be shear force at face of support. Okay. Very similar to what we did in the beam. So it's the same thing. So let's find our shear stress. V will be equal to the VS over B. Some book just say big V. It's fine. All right. So 27.6 times 10 exponent 3 over our B is 1,000. All right. And our D is what, 170. So this will give us 0.16 newtons per millimeter squared. All right. Again, check if this is supposed to be the minimum of 5 newtons per millimeter squared or um, 0.8 square root of FCU. All right. And the 0.8 of square root of 30 should give us so square root of 30 times 0.8, and we get 4.38. All right. So 4.38 newtons per mm squared. And since our maximum shear stress is less than um, one of these, we are good to go. Means that we can still go ahead and then calculate our final shear stresses, right? Because then this means that failure is governed by diagonal tension, not diagonal compression. Now let's do 100 AS over BD because we need to find VS, right? Uh, to find VS, which is the shear stress from the concrete. Sorry, VC, right? Shear stress from the concrete. So this becomes 100. Our AS that we had was AS was 523. All right. So 523. So 523 over 1,000 times 170. Okay. So this will give us 0.31. Okay. Then from the previous, so if you go to um from table I think there's a table with table 5.1. I'm just gonna bring that table up again so that at least it makes the discussions a bit more straightforward. So that's supposed to be table 3.7 in the BS code, all right? Okay, so table 3.7 from the BS code, take note of that. All right. Oh, no, not this table, sorry. I brought the wrong table. Forgive me. This table is fine, but this is not the table I want. I want the table that has the VC information, sorry. Okay, so what I want, but the table I brought earlier is fine. It's going to help me to come up with some um some. Let me reduce this guys a little bit. I hope I'm not running out of battery. I have 24% left. Okay, it's fine. We should be able to get far with it. Okay, so here we are with so let's look at our VC. Our effective depth is 170. So 170 somewhere here. Then our V or our 100 over AS is 0.31. Yeah, I have to reduce this. Otherwise, it's going to be too big. Don't need it to be that big over here. Okay. All right. So from table below, okay. So we are somewhere here, 170. And then we have 0.31. So somewhere here, 0.31. So we have to interpolate this for set of data. And if we do it, your VC will be 0.55. Okay. VC is 0.55. Okay. So let's come to this table. Okay. Which of this table applies to what we are doing? So which of these data sets applies to what we are doing so far? All right. So our V is 0.16 and our VC is 0.55. Is that what I had? Um, okay. So let's find 0.5 VC. All right. 0.5 VC, 0.5 times 0.55. Is that what I had? Yeah. So this will give me what? 0.275 maybe. Am I correct? Yeah. We can always cross check, but I think I should be correct. Uh, yeah, great. Okay. So we can see clearly that since V is less than 0.5 VC, no links required. So there's no need to do shear links in this case. So normally what we do as engineers is that when we are designing slabs, usually solid slabs, we tend to use smaller uh, depth, effective depth, all right, or even smaller overall depth of the slab so that we don't need to do shear reinforcement. All right. So you realize that for residential facilities, mostly the overall depth of the slab is about 150 millimeters. All right. Or let's say it's between 150 to 200 millimeters, but normally closer to 150 than to 200. All right. So I think with a BS 8110, when the overall depth is 200 and below, there is no need to check for shear because it would not require shear. But if it's 200 and above, there is a need to check for shear because it is likely that the slab will need shear reinforcement. Okay. So this is for the main bar, main rebar. Any questions? Did I hear something? Okay. This is for the main rebar. We need to look at the transverse rebar. All right. And for the transverse rebar, we normally use, for this type of beams, we use minimum. All right. So uh for, let's see, so check shear stress, number 6. So design, secondary or distribution. Okay. Since our Fy is 460 newtons per millimeter squared, uh, provide, my screen is gone, so provide minimum area. All right. So here, our AS will be equal to 0.13 BH over 100, or 0.0013 BH. I think I have that over here, and this is because our Fy is 460. Okay. If Fy is 250, we normally use AS being equal to, or AS minimum, since it's our minimum, will be equal to 0.0024 pH. But what we are using now is this one over here. Okay. So our AS will be 0.0013, a B of 1,000, and an H of 200. So the H is the height of the slab. Okay. And this will give us 260 millimeter squared per meter. So yeah, so I think so that's it. So you can go to the table, the bar table, and then since we are still using 10 bars, and we got an area of what? An area to be 260, we come back here and choose the one that is most adequate to us, right? So I'll go with uh I'll go with 250 and 314, because the 262 is too close to the 260. That's why. That's the only reason. There's nothing more to it. So I can say um provide T10 at 250 centers. So the area provided is 360 millimeter squared per meter. Okay. So I think the 360 we had, oh, 314. Okay. So 314, sorry. It becomes 314 millimeters squared per meter. All right. So this is how it will look like when you do the when you put the rebar into I think I had some, let me just copy this over here and bring the same thing just so that I don't have to. So now we are looking at the okay. This is 7 rebar detailing. All right. Okay. So the main bar will be at the bottom. I think I already mentioned that. So the main bar will be here. What happened to my color? So the main bar, this our main bar. That doesn't look straight, but forgive me. So this is the main bar. There'll be a bit of curtailing and all of that. We'll look at what these things are. So the main bar here. Let me just write something beside it so that this is a T10 at 150. Okay. Then we'll have some bars, and depending on the spacing, we can actually also calculate how many there will be. All right. So that's right here is a T10 at 250. Okay. So this becomes your rebar arrangement for um, more or less. It's a simply supported slab, right? So solid slab spanning in one direction. Okay. Oh, so let's take a break, then we'll come back and continue. All right. Recording. So let's look at also another so we're looking at, so I think the first one was to look at so this is a design of one-way spanning solid slabs. So this one I think was to look at, I mean, generally the example we looked at was simply supported. Okay. Simply supported example. Okay. So let's look at the continuous slabs. Let's look at so let's say continuous slabs. So this is solid slabs. Span in one direction or one way. Okay. All right. So for a continuous slab, a few things that we need to note that we need bottom reinforcement. Um, Also, bottom reinforcement is required within the span. And then top reinforcement is required uh, over the supports. All right. When so typically you'll see that the effective or the span to effective depth ratio, I know I always put effective in front. Span to depth ratio will typically be equal to 26. Normally, because of the fact that we have spans of this nature. So again, behavior and design is similar to beams. All right. So now, for example, if this is your slab, all right, and so the beams will be your supports, something like this. All right. If you have that case, depending on what the spans will be, you have to find the moment. So you find the moments in the spans. So basically we sorry, determine the maximum moment in the spans and over supports or supports. So when you find these, they can use them to pretty much do the bending design. So you do so for each span. If the spans have different moment values for each span, you look at the so for each span you look at the moment, and then you design. You find the reinforcement for that span. So that will be at the bottom. Then when you get to the when we get to what's the name? When we get to the support, you also do the same. But for the supports, the rebars goes to the top part. All right. So that's one of the key differences between between a simply supported one way and a continuous one way spanning slab. All right. The last time I think when we were looking at beams, if I remember it, and there were a few conditions that we were able to satisfy the last time. Um, where are you? Do I have it here? Was it that chapters, the lesson 6? I'm looking for it. I think it was something that we did the last time. Um, hopefully it's somewhere around here. Just want to copy that information so that we can have it. And let me look for it. Give me a second. All right. So with a continuous slab spanning one direction, um, we can simplify the analysis process, right? Normally, if you want to analyze this, you might want to use either the moment distribution method or the slope deflection method or some matrix method here and there to analyze this particular slab since it's continuous. And then you can determine the moments at the critical point, midspan, and then what's the name? Uh, over the supports. All right. The the other way, or which normally happens, is that you sometimes you come across slabs which have equal spans. So let's say the spans are equal. So this is a typical slab with equal spans. All right. So if that is the case, where you have slabs with equal spans, then if it's able to satisfy a few parameters, which I've written them here already, is that the loads should be uniformly distributed. That is one. So it should be a UDL loading system on the series of spans. And also the area of each bay, sorry, not each bar, the area of each bay, and we know what the bay means from previous analysis, right? The bay is a series of panels in one direction. So the area of each bay should exceed 30 meter squared. All right. And it should have 3 or more equal spans. Okay, at least 3 spans which are equal. And also when you find the ratio of the imposed the characteristic imposed load to the characteristic dead load, it should be at least, or it should be at most 1.25, right? Or it should not exceed 1.25. All right. And also our characteristic imposed load should not exceed 5 kilonewtons per meter squared, right? So these are the things that we need to take note of so that we can use an easier approach when determining what I'm looking for when determining uh, these types of beams. All right. Sorry, slabs. All right. I keep saying beams, but at least it's slabs. Um, that's something I want to cross check. So take a note, in cases where the spans are not equal or where the criteria above is not satisfied, then it means that we need to do a comprehensive analysis, all right, uh, of the structure. All right. So we have this information, the exterior support, the first interior support, and then we have the interior supports. Then we have also the exterior support or the end support. All right. So sometimes you see the word exterior on the word end being used, and it's right. It's just about the same. Okay. So for the moment, these are the equations for uh, the supports, or these are the simple equations to use to analyze the supports. Okay. So we have 0 points for shear. at end supports is 0.4 F, and then at first interior support is 0.6 F, and then at interior support is 0.5 F, whether left or right of the interior support, right? The same applies, and then for the moment we have the over support and over ultimate spans, all right? So the same approach is being used. Let's see how an example is going to help us to appreciate this better. So let's say example says design. Oops, says design. Um, the four span slab shown below. So I'll try and put that into drawing. Um, so the live load. All right. Let's 3 kilonewtons per meter squared. And then floor finishes plus what's the name? Ceiling load given us, let's say, 1 kilonewton per meter squared. Our FCU is 30 newtons per millimeter squared, or some would say MPa. And then the Fy is giving us 460 newtons per millimeter squared. All right, so I'm going to draw a plan and also an elevation of how this whole thing should look like. Um, so in plan, this is what we have. This is your beam. Um, so there are four spans. This is 1, 2, 3, and 4. So maybe there's a column here, there's a column here. Let's say there are columns at where I'm just showing this so that we know that it's a slab with beams and the beams are also on the columns. All right. So each one here is a span. This is 7 meters. And this distance here at the centers, each one is 4.5, 4.5, 4.5, 4.5 meters. All right, all the way. Okay. So take a note here. These are beams. These are beams. Okay, and that goes my okay, so we are back. All right. So beams. All right, great. So this is the plan view. Okay, so let me draw the elevation. Let's move it a little bit. Okay, great. So basically, whatever you are seeing, so there's elevation. and then above is the plan. All right, great. So since this is a continuous beam, let's look at our solution. So with our solution, first up, to look at the span to effective depth ratio. All right, we need to decide what that would be. Right, or into brackets, this is too thick. Into bracket, I'm looking for the effective depth ratio. Um, okay. So let's see, how do we do that? We know that the mean, all right, we're just going to work with just the basic ratio. Is span over the basic ratio. All right. And this should be, see if I'm recording. Yeah. So this should be equal to the span. The span is 4.5. So that's 4,500 for each span to the same span. The ratio is 26 for a continuous slab. So this is equal to, so 173. So 173 will be the highest depth we can choose. So it will be, um, so make, yeah. So if these 173, we can choose a value. Oh, so let's um, try D of 140 millimeters and then H of 170 millimeters. Okay, let's see how this goes. All right. So to the loads. Okay. So with the loads, we know that the soft weight will be equal to 0.17 times 24, where 24 is the specific gravity or weight of the concrete. So this will give me 4.08 kilonewtons per meter squared. So our total dead load will be, I think it was one from the partition, one from the ceiling, sorry. Yeah, floor finishes the ceiling, so it's one, that's 4.08, and that'll give me 5.08 kilonewtons per meter squared. All right. So with that, we can find the ultimate load. This is 1.4 times 508 plus 1.6 times 3 for the life load. All right. So this should give us I think 11.92 kilonewtons per meter squared. All right. So this still per meter squared, or in actual fact, this is supposed to be 11.92 kilonewtons per meter width. Yeah, I know it's crazy, but because we are looking at 1 meter width of the slab. So if you want to find this in F, right, the ultimate load in F, then it becomes 11.92 times 4.5, which is the span. So, that should give me 53.6 kilonewtons again per meter width. Okay. All right. So once we have that, we can now determine the bending. So we start, so just like what we did with the beams, we take each span, we take each support, we find the bending, we find your M, you find your AS, and then you do all of that. All right. So basically that's what we do. So let's look at three bending. So okay. Again, this particular beam satisfies, or this particular slab satisfies all the conditions we had up here. All right. So it satisfies all these conditions. All right. So because it is satisfying all these conditions, we can use the simplified equations below in the space to do our analysis. Take note, if it doesn't satisfy the conditions, you have to do the analysis from first principle, use moment area method, moment distribution method, slope deflection matrices force method, or the three moment equation method. All right. So here we go. Let's look at bending. Let's start with the first bit. So let's look at the first span. Okay, so the first span, if we go to the first span, we are being told that our moments in the first span. So this is the first span, or the first interior span, or near middle of end span is the same as first span. All right. We can look at it that way. All right. So we are told is what 0.086. So our moments from the first span, or which is the should I say the end span, so that we know is that is the end span. Our moment is 0.00 0.086 FL, and this is equal to 0.086. Our F is 53.6. The L is 4.5, and this will give us 20.8 kilonewton meter. All right, so 20.8, and then so you can again you can check. So this is for one, so this is for the first span. Maybe let's look at it as the first span to the interior span. So we'll do everything underneath this. All right. I don't know why this thing always happens. So that is 20.8. So we can look at so we find our moment. What's happening to my screen? Okay. To find our moments, let's look at a span to effective depth ratio, just to ensure that we are in the right path. All right. Most likely this slab would always have just tensile reinforcements. All right. There'll be some at the top, but they're also tensile in the way. So for over the support, I mean. So BD squared will be equal to 20 times 10 exponent 6, 20.8 times 10 exponent 6 over our B is going to be 1,000 times the D, which we chose to be 140 squared, and all of this will be equal to 1.06. All right. So we go to our thinking table The 3.10. Go to table 3.10. Our modification factor is 1.36. All right. I think it's table 3.10. Let me just cross check. I don't want to go all the way up there and look for it. Yeah, table 3.10. Yeah, so 3.10. Great. So it means that our limiting span to effective depth will be the 26 times 1.36. So this should be equal to 35.3. Great. Okay. And then whatever we are working with would be the actual, which will be the 4,500 over our 140. And this is 32.1. So it's great. All right. So our 32.1 works. Anything lower, and we will be hitting our limits. Okay. So here, I can put here that D equals 140 mm is adequate. Okay. So it's always good to do this check so that you don't end up with a case whereby your effective depth is not adequate. Okay. So now let's look at the bending reinforcement. So K is equal to M over PD squared FCU. So that's 20.8 times 10 exponent 6 divided by B of 1,000 times a D of 140. We just checked is fine. So times 30. And this should give us 0.035. This is less than 0.156. Mostly you end up with this solutions, okay? And because of the low values of K, your Z value is mostly 0.95 D. Okay, so take note of that. So our AS, which is M over 0.87 FYZ, will be equal to 20.8 times 10 exponent 6 divided by 0.87 times 460 for the FY. And let me put this answer over here. 0.95 D will be 133 millimeters. Okay, so times 133 here, and this should give us 391 millimeter squared per meter. Right, you see me writing this a lot because we're looking at per meter width of the slab. All right, then you go into the table we were earlier, the table to check the area with respect to the spacing. All right, so that right here. So let's say we are using again T10. So T10, we had 391, so we can choose 393. So our spacing is 200. It works. All right. So we can say so we can come here and say provide T10 at 200 centers. All right. Where your ASP will be 393 millimeter squared per meter. All right. So that's how we do it. Okay. So you have to do so pretty much, let's say, so you guys should, let me say complete. I'm looking for a ticker. Okay, so complete. Similar calculations for the interior spans and supports. Okay. When it comes to shear, this is going to pass in the sense that you wouldn't need to check for shear. I mean, you wouldn't need shear, you can check for shear. You wouldn't need shear because V will be less than 0.5 VC. So no need for shear links. Okay. So this is supposed to be the bending reinforcement or the main reinforcement. All right. So for the transverse, or what we call the secondary reinforcement, um, we know that K, since our Fy is 460 newtons per millimeter squared, the area for the secondary reinforcement is going to be 0.0013 BH. So 0.0013 times a B of 1,000 times an H of 170. And this should give us 221 millimeter squared per meter. Okay. So here, going back to that, the spacing table and then the area table, they becomes provide T10 at a space of, let's say, maybe 350 millimeters centers. And yeah. So whenever you have a main reinforcement, you provide this secondary reinforcement. All right. So if you do the calculations fully, you would realize that then this becomes, so if this is your slab with its corresponding beams, so you would have on this edge, maybe all the way, you can have, right. So this will be your rebar arrangement. And depending on which spans you are looking at, they'll vary. So maybe um, so here, what we had earlier, uh, right here, we had, I think it was T10 at 200, right? We had that from our calculations. If you calculate the one in the interior span, you would end up with maybe uh, T10 at 250. And then the same way also, so the first interior span is T10 at 250, and the other interior span is also T10 at 250. Okay. So try and do that. There, do the calculations, and then let's see how things end up. Okay. Then when you do over the support, you also get, so you have your supports bars because they're supposed to be there to help with the, what's that name? I mean, tension moment will be at the supports. So they'll be up here. So in the same way, this here and this over here will have, this will be, this is going to be maybe T10 at 200 if you do the calculations. And over here we have T10 at maybe 250. All right. Then here at the end support, since the moment there's zero, we are putting minimum reinforcement over there. So here it would be T10 at 300 millimeters. All right. Then we have the secondary rebars, which will be right there, which is what we just calculated for when we're looking at the minimum. Okay. So they will always appear where your main rebars are. Okay. Or something like that. Okay. And that one, the oops. The secondary rebar, most I think we have what T10, so T10 at 350. Yeah. So all the secondary rebars will have that T10 at 350. Yeah. And this diagram here represents our bending and all the detailing for the beam. Okay, sorry for the slab. Okay. So there are two more we need to look at. Solid slabs spanning two directions. So we look at whether they're simply supported or they're continuous. Okay. And the code has made some provisions to that. So we'll try and look at that as well. All right. Okay. Thank you.